Ravi sir, we can start. Ravi sir, we can start now.
Okay, okay,
Okay.
Anand,
Anand,
okay, sir. Good
Sivan
morning,
sir,
everyone.
okay, yeah, okay, Anand, start.
Okay, sir. Okay.
Yeah,
Okay.
okay, please.
Good morning, everyone. Welcome you all again on third day in MATLAB-based solution for smart cities MSSC 2025. Myself, Anand Vardhan Pandey. It gives me great pleasure to welcome you all to today's expert lecture on solar electronics design ecosystem, DC-DC and DC-AC power conversion. We are honored to have with us Dr. Aman Jha, a distinguished professional in the field of smart power electronics. Dr. Aman is working with Havells Noida campus as a GM R&D Lightning Electronics in Center of Research and Innovation Department. In current role, he is associated with smart and connected electronic product design. His association with several organizations as a people manager and technical professional having more than 21 years of experience with reputed MNCs in smart power electronics design. Holding sound academic profile, PhD power electronics and electric machine drives from IIT Delhi, MTech power electronics and energy system from IIT Bombay, business management from IIM Bangalore. Other voluntary work, he is associated with reviewer of reputed journals, technical speaker of reputed forums, faculty development scheme trainers, senior member IEEE, IAS, PES, and visiting professor at NIIT University. He has more than 65 reputed research publications in IEEE and equivalent journals and several free design available on the different technical forum. Today, Dr. Raman will be sharing valuable insights on solar electronic design system, which I'm sure will be enlightening and thought-provoking for all of us. Sir, please, over to you, sir.
I think. Thank you, everyone. So, can I start?
Yes,
So,
sir, please,
yeah, 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 yeah. So, hope my screen is visible to everyone.
yeah, it's visible, sir.
Okay. Just I'm checking the movement. It is not moving.
Hmm.
Is there any reason it is not moving?
Yeah, it is not changing, sir. PPT is not changing. Right.
Yeah, yeah. That's is it visible now?
Yeah, it's visible and it's moving also. It's changing also.
Okay, good, good. Thank you. So, so due to limitation of bandwidth, just switch off my video. Thank you.
Okay.
So thank you everyone. Thanks for the team to call for this discussion. So this is the topic for today's discussion, that is solar electronics design ecosystem. And so here in power electronics point of view, here we have to work on DC-DC and DC to AC power conversion. Let us start from the basic. So first we will discuss about the PV power characteristics. Basically this is the source, and we should understand what the source are, and then we have to load that. So then we will discuss about the PV loading techniques, what kind of PV loading techniques will be, and how to get maximize load, that is the maximum power point tracking. And then we will go through the different kind of power converters in PV applications, and start with the DC-DC converters. Then we will discuss about the inverters, then their types. Inverters are the long list, and then finally we will discuss about the how to interface inverters from the grid. That is all about. Due to the time limitations, so we will not go in detail of the all converters, inverters, and design that, but I will discuss about the how it can be, and what's the business needs, and what's the role, as everyone knows that. So these days we have almost 100 gigawatt of installation of the solar. We crossed the 50% of the power, so need from the renewables. So if just starting quickly start to the technical side. So if we go to the PV power characteristic, hope screen is there. Second slide is moving. Anjani,
Yes, sir.
yeah. It is screen is moving.
Yeah, it's moving, sir. It's
Yeah.
fine.
So coming to the PV power characteristic. So fundamentally, PV electrical characteristic is I versus voltage. If we see here, this is the completely non-linear curve. So as per the curve says, so we have the maximum power point. So there we can get the maximum outcome. So this is the behavior of the photovoltaic cell. So for getting the maximum power and outcome of where it is there, so this graph will help. This is generic graph, everyone knows that, but it is the basic part to understand with. So but if we as per the solar basically irradiance, whatever the sunlight is coming to us, uh, their graph is keep on changing. So if we see here, there are different graphs as per the irradiance. So if irradiance as per standards, 100 watt per meter square is the irradiance of a standard irradiance. So that's, if we see this will be the keep on changing. So this is the challenge for the designers to optimize that. So if you see here, as per irradiance, power level is also increasing, current is also increasing, and voltage change is slight. So similarly, in terms of the cell temperature of the PV cell, if we say, it is if temperature will increase, for example, if someone is telling at the mid sun condition, there should be more means power, but it is not the case, because as per calculation, so per 10 degrees Celsius rise of PV cell, we will get the less than 5% of the power. Similarly, with the sunny days, there is the different cloudy sky. This is basically why I am explaining these things. These things need to be take care in terms of the designing of the electronics for the solar utilization, maximum solar utilizations. So this graph just I have taken from reference from somewhere. So if we see here, even in sunny days, there is the differences in terms of irradiance and the cell temperature. So finally, if we go to the cloudy day, there is again the large variations. So in summary, if we see here, so we have the solar panel. So but we have to optimum utilization in terms of the sunny days, in terms of the cloudy days, in terms of the temperature, in terms of their radiance, and all four are variables. We are not measuring that in the field, and but we have to take care all variables to get the optimum utilizations. At the end, if we see here for this section end, so if we see here, this is the maximum PV power generated. If we see, so typically one crystalline solar cell will provide 4 to 5 watt power at a standard test conditions. And so normally in the market, 250 watt to 300 watt panel are available, but at this moment we have also availability of 800 watt panel of single unit, but it is slightly higher price. And further we need to increase the power, so we have to go with the arrangement of the PV panels. So this is the first way of arranging the panels, that is basically putting all in the series. If we see the standards, US residential standards, so we cannot add more than 600 volt as per the panel, but as per IEC 1000 volt. And there is the new scale is coming up, that is for 1500 volt. This is the calculations for means installation purpose. So number of cells multiplied by the maximum power, and also multiply by in terms of the maximum voltage and the open circuit voltage. This is the BOC rating of the string, maximum voltage VP of the rating, and power maximum of the ratings. These things will be taken care in terms of the designing the PV system. In same way, we have to go with the parallel combination to increase the power level. By adding in parallel, we will get the higher current, and by adding the series we will get the higher voltage. In combination of the voltage and current, we will make the typical solar power system, so that this based on this calorie, so that we will get the maximum power. For example, if less than 5 kilowatt of case for the single phase, more than 5 kilowatt could be the three phase case. So this way we can arrange the series parallel combination and make the panel for the design purpose. So in summary of this section, the power output of the PV panel basically depends on where the device is operated on this characteristic. It is already discussed, it is nonlinear. Namely, basically we can say this as a loading of the PV panel. Then the PV power characteristic of PV panel is not constant, as we said, and also we are not measuring in the field. They changes continuously in the day as per the incident solar radiations and the temperature. Also, PV power output can be increased by, as discussed, series and parallel combination and make the PV array, and for application purpose. Again, I said these are the discussion point of PV characteristics. Now coming to the how to load that PV. In this section, we will discuss about how to load the PV. So first, that is very easy part, that DC loading or resistive loading. So for example, DC bulb heaters can be connected. If you see some Chinese products that will be available in the market, they just use direct solar panel and use up the power. But if you see here, there is the, as you see again basic, it will work as per the basic load voltage and current. If load voltage and current, for example, so if load will change, then it will be not a good solutions. This is because if we see here, this is the graph. What happens when the irradiance of temperature changes? If temperature will change, you will get the lower irradiance, and then the voltage will be less and power will be less. So maybe your load will suffer. At the same time, if you have more, if you put the more panel, more voltage, again that will be load side. It will be create difficulty. This is the one case of connections, because DC PV is fundamentally DC voltage, and at the same time, if we connect with the battery, so again here is the problem. So battery voltage should match with that. If battery voltage will not matching, then it could be power will come from means the battery to, and it will drain in the panel, and also maximum power point is not able to get. So now power electronics coming into the picture, because we have panel available and there is a bit in between the system, because DC fundamentally PV is a DC, and but we cannot get the optimum use for the load. Then we have to go for active PV panel loading and maximum power extraction. This is the way in between. If you see here, this is the power converters that will operate in active mode, so that get the optimum utilization of the solar and also the load conditioning as per their need and their use case. So, yeah, just a minute. So, in summary, if we see here, the power output of PV device depends on the electrical characteristic of the panel and the load characteristic of the terminals. The current and voltage rating of the load must be compatible and well matched with the PV panel in order for the load to operate safely and efficiently. Passive loads such as DC loads and battery are not able to track the MPP under changing environmental conditions, and that's the reason we have to go with active load conditioning, and that is the power converters, power electronics coming into the picture. Now, summarizing these two sections, as we discussed the PV panel characteristics and their behavior in terms of the sunlight, in terms of the radiations, in terms of their temperatures, and further the load conditioning. What are the loads are important? If load is DC, even DC load, we cannot connect the panel directly, and there is a need of power electronics. In these two sections, this is the basic sections. I've just quickly covered that. Now the coming to the next thing, optimum utilization of the panel, that is named as the maximum power point tracking, or maximum MPT we can say, or maximum power point tracking, MPPT we can say. So what is the maximum power point tracking? If you see here, this is the graph already discussed in the first slide. dP by dV will be 0, that is the basics on the 12th. So that is the maximum power, and that's the ideal condition we have to get. So in so whatever the microcontroller we are using or DSP we are using, that's the tracking that voltage, and finally it is the power, so that we get the maximum power, that is the optimum gains, without realizing the actual condition of the field. Is it cloudy days, or is it temperature is higher, lower, or whatever the range that. So our microcontroller or our power converter will operate in such a way we get the MPP. But how to get? This is the way. If you see here, this is the flow chart. If we see just again, this is the basic how to get that. So just optimizing. This is known as a well-known technique, that is P and O, perturb and observe technique. So by using this, basically this is the simple and low computational demand. So we just track the P power by measuring the voltage and current, and then if power is at a higher side or lower side, depends on their optimum case. If it is higher side, we again go with decrease, increase, and in that way we track it is the by use of the microcontroller or DSP, depends on the complexity of the design. So we can go with, and it is very generic, but here trade-off is between speed and accuracy, because we know there is the cloud movement and all. So there is the speed and accuracy, the challenging every time. I can track wrong way. If we track the wrong way, we get the wrong power, and optimum utilization will be not there. This is the checkpoint here to design a best MPPT controller, and everyone is working on this. So fundamentally, it is hill climbing methods, and there is two methods as I discussed, that is P and O, and other is the incremental conductance method, that is DI by dB and dP by dB. And based on that, we will not go on detail of that. And third is static method, that is VI sweep method, that is more optimum, and it is some people using the fuzzy logic and some methods to use and create the MPPT based on that. What are the limitations? Because if you see here, this is the partial shading conditions. There are three maxima, minimum, maxima. So this is the challenge. Partial shading can lead to multiple power peaks in the models and multiple bypass diodes. So here local MPPT and the P&O and the incremental conduction methods can track the wrong peak. So here we have to go with global MPPT scheme or VI sweep methods are needed to basically needed for the global power peak. This is the again active PV panel loading and maximum power tracking. These methods here, This way, we have to use a power converter for tracking the MPP point of the panel for a wide range of irradiance and temperature conditions. The load is variable and can handle the maximum power output of the panels. So already discussed this part. So in summary, we can say maximum power point tracking algorithms are used to actively search for the maximum power that can be extracted from the PV generator at any given time without knowledge of the actual irradiance and temperature condition. As I said, the variable is not available for the measurement. So we are working by just voltage and current being a designer. So we should keep in mind. So local MPPT algorithm have limited tracking accuracy in partial shading conditions. The global MPP maximum power point can be found using the IV sweep methods as I discussed. However, it cannot be used with high frequency. It is a little bit slow because it depends basically track the voltage and current. That should be more. And basically it implemented. We have good skill set in terms of the power electronics as well as the software development, basically embedded firmware development in term for the MPPT tracking algorithm. So in summary, after closing this session, basically first we discussed about the PV characteristics, then different loading techniques, then the optimization by use of the MPPT. Now coming to the power converters. What are the power converters used for PV applications? Of course, first will be the DC-DC converters, and in block diagram if you see, power will be in, power will be out. This is the block diagram. That is the very basic. And first will be the DC-DC converter. DC-DC converter normally used for lighting applications and other applications as well in battery operated systems and battery storage and all. So in DC-DC converter, input is DC voltage and input, and DC current and DC voltage both are the input. Output also we will get the DC voltage output and DC current output. Fundamentally in this kind of converter, so boost converter, buck boost converter can be used for commercial applications, and it is in the market. These three only in popular because as per the cost and other consideration is there. In DC to AC conversion, this is very much in the market and very much popular. So here input is DC voltage and current, and but output you have the AC. So that's the reason it is known as a DC to AC converter. So inverter, we can say inverter. So the inverter will convert DC to AC, and this is fundamental for you. So stepping down, now coming to one by one of each. So first converter is basically buck converter. So how buck converter works? Buck converter, there is the one active switch and one diodes is used, if you see here. So that is the fundamental converters, and it is much popular in battery charging because normally we keep battery voltage higher and panel voltage higher and battery voltage lower. So buck converter is popular. And the reason is buck converter is fundamentally, if this converter short circuit protection is by default, so that's the reason it is much popular. And so here if you see here, diode in one condition switch is on, other condition switch is off, and diode is work as a freewheeling modes. This way this buck converter operates. And semiconductor switches in this domain, mostly IGBT and MOSFETs are used. For higher wattage, higher power applications, IGBT is used, and for mid and lower wattage, MOSFET is much popular. This is because MOSFET, you need very less current, the voltage driven device, and quickly it charge and discharge, and so very quick operation. So switching operation can be at higher side relative to IGBT, but higher power level IGBT is much popular. So for solar electronics, mostly these two switches are in use for DC-DC converter and DC to AC converters. So for selecting the right switch, because this is the cost, we have to go for the cost effective devices. So searching the right MOSFETs or right IGBT, selecting the right components is very important. And you have to go through the all major semiconductors manufacturing, ST, TI. Infineon and ST are more popular, and many more Chinese are also available for low wattage or lighting and other applications. Those are is low cost, and it is in use due to the price of the power supplies, charge controller and all. So just if you see here the means just a graph I have shown, there is two modes of operations, means saturation modes and cutoff mode. That is the switching operation. MOSFET here, switch here used as a means switch, so no active mode of operations. So that's selecting the switch, selecting the right gate drivers is the important criteria for the power converters design application. So if realization, if you see buck converter is V2, means output voltage is multiplied by duty cycle to the input voltage again. Here we get the higher efficiency, close to more than 90%, 90, sometimes 97, 98 also. Some places as current required in more, so we have to go with the synchronous rectification. So this diode will change with the another MOSFET or another active switch. So it will create higher efficiency. Another area to work here, if as per mid to lower power rating, so these switches are can be used as a GAN, or for higher wattage or high temperature application, it can be transferred to the silicon carbide for optimum size and other applications. So in this session, we cannot go in detail of that, but this will give you some idea to select the wideband gap switches to optimize the efficiency, optimize the size, and create the new SKU for the applications. And this is I am emphasis is more here because this is a much more commercial things, and buck converter is much more popular in charge controllers or means MPPT charge controllers for battery charging and all. So here you have to go with it because some places this switch can be used as a means ground side, lower side. So there you can, that is known as inverse buck. So that will be some places for lower wattage. This can be used as a P type, so that driving is easy for the those MOSFETs. So again, here inductor selection is very important. So how to select the right inductor for so right price is again very much important. So saturation characteristic of the inductor and all, and their means availability is also very important. So basically, fundamentally, these three are the major design. If you go any basic book, you will find out the design calculation. So for boost converter, same thing is in the reverse direction. So we are getting the higher voltage, and some places you can see here buck boost kind of techniques can be used. So and in lighting, so people are using like that sometimes because in night same switch can be used as a buck or boost converter by exchanging that, so that there is the only two switch and you can get the higher voltage also and lower voltage also, depends on the use case. So their optimum utilization of that. So buck boost converter is transfer function is like this. Output voltage will be transfer 1 by 1 minus d, that is duty cycle. Again here selection is very important, as I said, that is repetition of that. Here again you can go with the wide band gap devices, depends on use case, and synchronous boost as per the use, lower voltage and higher current. And at the same time here inductor design is important. So if you optimize this inductor and this inductor, so same inductor can be used as a buck or boost. So only these three will be one, and you can make the power converter buck and boost as per the use. For example, lighting, boost converter used for the driving the light, and the buck converter used for charging the battery. So daytime they charge the battery, and night time they drive the LED. So in buck boost converter, so this is the buck boost converter again. This is again basic things. So if you have gone through your MTech course, so output voltage will be multiplication of D by 1 minus T. Again here inverse buck boost is used some places, or but and this output voltage to minimize the output voltage in terms of the negative. So in summary, there are more converters, say P, too many others are there, Gita and all that, for academic purpose or research purpose. But in commercial purpose, these two are much popular: buck boost and boost converter. So DC-DC converters step up, step down in some to get the as per the need of the load or source. Source here is the panel. DC to AC converters can generate AC as discussed, and MOSFET and IGBT are the switches for these applications. Of course, diode is there. The converter switching and operation is controlled by PWM techniques. So for solar, to particular to the solar, so coming to DC-DC converters for solar applications. So as I discussed, solar charge controller, so basically MPPT solar chargers, if you see, and this picture, as I said, in lighting application, this is much more popular. So here functions are MPPT controller, DC-DC converter, and I just repeating that battery charging. It could be advanced charging, depends on the battery and their battery. They're like lithium ions and all. Then the protections is needed, load switch off conditions should be needed, power conditioning and safety. These are the basically functions you have to take consideration for the designing of the power converters for the solar charger applications. And MPPT solar charger controller is normally used for off-grid solar power systems. Off-grid means there is no grid available, and typical application, if you see here, solar home systems, standalone systems, and water pump. Solar pump is another big area people are using, and that is also agriculture side, is big business. And additional standalone inverter is required. For example, if you are working with inverters also, so first stage there will be the DC to DC converters, then DC to AC inverters. So we will discuss that part also later. So then second application is power optimizer. Power optimizer, I think you know that part. So power optimizer is basically, as we discussed, there are multiple panels and we have to get optimum use case or maximum power from the panels. So MPP, this power optimizer will do that. So there are different types. So I will share the slide as well to the team so they can read it. So different types of means power optimizer in the market, and those are depends on the use case. Fundamentally, they will help in terms of the setting. Different module orientations in modules are orientation are different. Some manufacturing process, weather variability, and some maybe in panel, some panel fails and it misbehave. So that case power optimizer helps. But disadvantage here is we have higher initial cost, and if you add their price and their cost and their reliability as well, so this is not much popular in residential and institutional applications, but maybe power stations they are using due to the higher power level. So again, DC-DC stage, I said in earlier slides, it is also used for inverter sections. So before inverter section starts, there is the DC-DC converter. So DC-DC boost converter are often here is used to basically integrated for three-phase PV inverter for boosting the string voltage up to 600 volt. So means higher voltage and lower current is optimum choice for electrical engineers to reduce the means loss. So normally here also what we do, we take the panel. Normally panels are SCLV based, so we make the series parallel, but and as per the voltage changing, so there is the dynamics, so we make the boost converter so more than that string voltage of the panel, so that inverters will be able to get input fixed. So this is the requirement. And so in the inverter, PV inverter case, first stage is the DC-DC converter. You see here, this is the DC-DC converter. Mostly it is a boost converter. So boost converter is used to make input voltage of the whatever the input coming from the panel to fix at the, like in the AC-DC converter, there is the bus voltage. This is here also, this is named as the bus voltage. Bus voltage to be fixed up to 600 volt, depends on the panel voltage. And this is the one use case of DC-DC stage in PV inverters. So in summary, if we see in the DC-DC converters use case in MPPT charge controllers and power optimizers and intermediate stage for the inverters. These are the three use case in solar electronics for the DC-DC converters. First is the charge controllers, another is the power optimizer, and third is the intermediate stage of inverters. And the power optimizers are module level DC-DC converters that are used to reduce power mismatch and increase system energy yield in shaded PV strings. This is the, in nutshell, in one line, if you have to say, this is the use of the power optimizer. And DC-DC converter stages are used to extend the voltage operation range of PV inverter and allow for multiple independent inputs in PV string inverters. So this way we can summarize this section. So DC-DC, now we are concluding for the DC-DC converter sections for the PV application. So in summary, we need only three kind of power converters for DC-DC, that is buck converter, boost converter, and buck boost converters. All are non-isolated converters. And the use case is, one is charge controllers, another is the power optimizer, another is third is the intermediate stage of that. And design side, we have to think about the selecting the right switch. Switch is again fixed here. Switches are MOSFETs and IGBT and diodes. Diode, again, you can select right diodes as per the use case. It could be Schottky, ultra fast diodes are much popular. Normal speed diodes is maybe efficiency wise that will not. Again, in MOSFET and IGBT selection, we have to think about which IGBT or MOSFET you are using, and it depends on their cost, depends on their use case, depends on their switching patterns. Again, in inductor design is the magnetic design. The magnetic design is very important. So how to design the magnetics is not not, I can't say it is a tough task, but it takes the lot of iterations and calculations to optimize the inductors. Now now coming to the inverter sections, PV inverter basics. So inverter size, as I said, single phase inverter. Single phase inverters are okay. Single phase inverters are basically in use up to 5 kilowatt applications, and fundamentally this is the basic thing. So there are 4 switches. It could be IGBT, it could be MOSFET, are in H-bridge combinations, and we get the output VAC here. This is the typical way of operation. If you see here, in one side this will on, and other case another size, the second cycle will be there. So again, I will not go in more of the how to work on this and design part of the inverters. So this is the typical configuration for single phase inverter. So this is the first cycle, this is the another cycle, and this you get the final output. This is the AC cycle. So by using this these two filters, you will get the smooth AC. And again, this is the optimum requirement. Again, here also we have to work on the THD and their requirement, so that less than 3% THD is used for the grid tie inverter kind of applications. So again, I will go to the detail of that for just understanding that the single phase already understand. So in three phase, so we have 6 switches, and again this we know this three phase operation, we get the three phase output as per the use case of that. So here if we see means there are two kind of inverters in market. One is with transformer based, another is transformer less. Transformer less, normally they can say silicon based means inverter, and transformer less inverters. But transformer is needed because it will give you the means isolations. And stage by, if you see here, this is the stage of inverter, the switching operation. Then you have to put the filters, then the main 50 hertz transformer, and it will be the load. Normally it is normally advantage here is we get the galvanic isolation between the PV generator into the AC grid. That is the good part, but at the same time, your due to the main transformer is the bulky and your weight is more, so you get the increased size and weight and cost will be more. So this is the reason nowadays PV panels are rated for 1000 volts and more. So normally we go with the grid means without transformer. And this is again the just showing the how the means transformer in use, how transformer do first stage, second stage, finally the flip, and you feel finally get the uh, output at this level. And coming to the transformer-less inverters are much popular. Being power electronics, here you have more work to in terms of the galvanic isolation is not there, so you have to take care and make some RCD arrangement so that if some leakage, earth leakage will be there, there should be not failure in fail of the system. And there are a lot of topology. If you go and the literature, Herrick converters and all our inverters are there to make transformer-less inverters feasible for the market. And it is at the single stage, basically single phase. Normally in Herrick converter, normally 6 switches are in use to isolate the noise, as well as the earth leakage. So in main component, if we see the inverter side, there is the, as I said, earth fault conditioning, MPP, maximum power point regulations, central control and command, residual current measurement to check the ground fault if any, and grid monitoring. So block wise, these are the blocks you have to work on to design inverters for grid kind of applications. Just I'm taking one call, sorry. It's urgent. Hello. Hope I'm
Hello.
audible. Yeah.
Yeah, yeah,
Sorry,
yeah.
the recall. Yeah. So, we are at the main components of inverters. So, for design perspective, so these are the 6 blocks to develop for the inverter design. So, in terms of if you divide this in terms of the software and the hardwares, so in hardware side, DC to AC inverter power stage, RCD, and EMI/EMC filters. These three are the major blocks for the hardware engineers. For software perspectives, so the feedback controls, embedded controls, that's in terms of DC to AC and DC-DC stage, and grid synchronizations, and then the leakage, ground current monitoring, and their decision making. Whatever that is there, then you have to treat the things. That is also someone, also the in terms of MPPT tracking is the work for the software. So we cannot say here software, that is the embedded or firmware kind of thing. And PV system performance and yield monitoring. So for example, whatever is going on, maybe your product in the field. So there is the dashboards and that data is coming there. So how much you are getting the power, how much the unit, how much carbon credit you are getting. So that those dashboardings and interfacing with the external weather sensors or services for conditioning and monitorings and diagnostics. These days AI is much popular. So and so here we have to use in terms of the PV array diagnostic and the complete system monitoring. So overall, this is the major components, and this is the application side and design side to work with. So in summary, efficiency is important, conversion efficiency, MPPT tracking efficiency, as already PV inverters, full bridge based switch topology. I think this already I discussed here more. So just skipping this. Now coming to the different types of inverters in the available in the solar electronics applications. So first is you can see this is the micro inverter. As name says, micro inverter means power level is less than 1 kilowatt, but these days up to 1600 watt is available as a micro inverters. As size is reduced and efficiency is more, so that's the reason up to 1.6 kilowatt is used as micro inverters. And as I named is there micro inverter, so it is the back of the panel. So and there is no separate location of that. So each PV module has their own single phase inverters and MPPT. So and that way this is small and monitors very quickly and very highly efficient way. But at the same time, power level is not so high. So here advantage is same as power optimizer we discussed, similar advantage. So no string mismatch losses, high modularity, easy module level shutdown, use of standard AC installation materials, reduce cost, no need for string diodes. As I said, there is as number of string diode is more. Maybe if system is 3 strings, 3 diodes, then you will get the 3 maximum minima of the MPPT. So that's complexity is not there. Disadvantage, lower efficiency compared to power optimizers, more difficult maintenance because every time you have to open the panels, work on this and cost wise, if you in terms of the power, cost wise it will be higher side. String inverters, as in here name state. So strings basically, if you see here, so all are connected in strings. So this starts from 500 watt up to 3 kilowatt, and each individual strings will be at voltage level. So only PV module will same orientation, tilt, freedom, and from state should be connected in the same PV strings. As I said initially also, orientation is important. There, if some shading is there or not, you have to these four variables need to take care for one string, and panel should be connected so that we will get the higher voltage and lower current and overall higher power at higher voltage. This is the concept of string inverter. So only PV mode, if string voltage is high enough, then no voltage boosting is necessary. So as I said, means boost converter is needed. But if you add the even multiple panels in series, you will get the optimum voltage. Then sometimes it is not needed, but depends. If you are again going with very other higher voltage, then it is needed. And as per microinverters, in relation to macroinverters, this is easier to install and reduce installation cost. Coming to next, that is multi-string inverters. Here, multi-string inverters is inverters are connected in parallel and series as well. So here, utility PV use case is utility PV, commercial PV, residential PV, wide maximum power point tracking, and this is basically we can say this is much more popular in residential applications for kilowatt ranges. Okay, and central inverters again it is very high power level. You have to create, and power stations normally they use and the power rating in the range of 50 kVA to 2.5 mega volt ampere. And again here input voltage up to 1500 volts, that is the new norms coming, and we can go up to 1500 volt. And here MPP tracker is sometimes is not possible, so that's coming under the disadvantage. Power losses due to common MPPT, power loss due to module mismatch, losses in the string diodes, lower reliability of the whole system. If any one fails, it will be done. These are some disadvantages, but this is also in use for larger installations. So for better utilization of central inverter, so PV inverters with power optimizer. So this is again complex system, but you get the optimum use case. So optimizer is there, so they optimize the power from the individual panels, make the system optimum. And this category standalone PV inverters, here there is no grid, so here it is in used as a off-grid application and AC load application. This is again basic thing. And standalone inverters, if you see, this is again in residential case. So load is there, and this combinations, this is in huge application case. So coming to the specific part, that is the grid tie inverters. Grid tie inverters also named as a grid follower inverters. Grid follower means it follow the grids as per their requirement. They manage the voltage and frequency and match the grid requirement. So here major requirement is synchronization with the grid voltage amplitude, phase, and their frequency. This is the use case, and this is important. And also islanding, if any islanding case is there, so you have to off your means there is a norms of your inverters within 2 seconds, and there are above 5 kilowatt normally three phase in used, and less than 5 kilowatt up to 5 kilowatt are single phase. And if you see this is the big work for Indian market, so there are a lot of inverters are coming in this category from the China. So here work is more to develop our own inverters. So here if you see function and requirement size, inverter is there already, but you have to work in synchronization side, synchronizing the grid amplitude, automatic startups, synchronization in presence of sufficient insolations, and automatic shutdown, as I said, that is as per the islanding effect. And the grid tied PV inverter. Just if you see, this is grid tied, this is the grid tied. It means this is also known as hybrid inverter. So hybrid inverter is basically there is the, if you see in the optimum case, there is the need of battery. There is the panels, battery, and also the load and grid. These four are the ecosystem in between electronics has to go over. Means if I say in one word, so there is the panel, panel power will come unidirectional. Then the battery power will work as a bidirectional. It can charge and it can give the power. And grid, again grid can be take the power or it can be give the power. So bidirectional. And the fourth is the load. Load again is the sink. It will not give you any power. So there in this ecosystem, if you see in the grid tied PV inverters, there are four things. So your electronics should work in such a way, and they optimize all four. Whenever panel is there, power is there from the panel, it take the power from the panel. If battery is not charged, it charge the battery or supply the power to the load, and also excess power they can supply to the grid. At the same time, if there is no sunlight, maybe 3-4 days, 5 days, so power should be come from the grid, charge the battery. If sometime power, maybe night time, it take the power from the battery, give power to the load. So this optimization is much more here. So this is basically if you go to the any marketing site, so there are 80% of inverters are GTI, grid tie inverters, and 10% inverters are basically uh, hybrid, and 10% are off grid. This is the pie for last year or maybe mid of or start of this year. So 80% is grid tie inverters, but grid tied inverters will be much more popular in near future because we have a large energy storage which we needed, and depends on the EV requirement all. So this is in growth stage. Here you can start working and develop the product. So this is the good area to work here. To and also complexity is there. Here power management of the all four sides, and this is the overall complete system you can say. So if you go to the literature, there are a lot of even in market it is available. You go in Chinese vendors or even in multinational companies, they have this inverter. But those inverters is not made for Indian grid condition, Indian load conditions. So here we have very big business will come up. So maybe you can plan this kind of inverter to be designed for India market. Okay. So in summary, we can summarize here inverters. So inverters are basically microinverters. As I said, microinverters are same advantage as power optimizers with cost savings on the string, cabling, and plug and play flexibility. String and multi-string inverters are versatile and used in a wide range of PV systems, from residential to commercial and utility scale. Multi-string inverters offer some of the system design flexibility of microinverters, but with a lower cost. Central inverters have a high efficiency and are designed to operate optimally in the utility scale if PV plants where shading and string mismatch is minimal. Standalone inverters are used off-grid applications and can form a control the local AC grid. Grid-tie inverters are designed to operate it linked to electrical grid and must meet a series of safety and power quality requirements before they are allowed to connect to the grid. Now coming to the last session, that is the interfacing part. I have made this as a separate session to how to interface PV inverter with the grid. So first we will discuss what the requirement of the grid operator. Grid operator basically they need power. Grid is normally infinite source of power, so they need power in terms of their frequency and their voltage and their means wave shape. Basically, their means we can say their phase basically. So PV inverters must follow certain technical requirements. You can follow the BIS and IEC norms. They have the means their standards is written. So before they are permitted to feed into the power supply grid. These requirements are necessary to maintain the stability on the electric power of the grids. So as per standards, if you say we are following in India IEC standard, and some country they have IEEE in USA, VD in Germany. But for India, IEC and now IEC converted the same norms we converted for the BIS. So we have our own norms. So we can read that and accordingly we have to develop the design. Then the main PV inverter grid code requirement covers this. These basically these three are the major requirements. First is the tolerance to grid deviations and response to abnormal grid conditions, power quality requirement, that is THD and voltage and all, prevention of standalone operation, that is islanding, as I said, islanding effect. So interfacing with the electric grid basic concept, if you see, so there are three things. If you see here, there is POC, point of connection, PCC, point of common coupling, and PGC. PGC basically point of generated connections. Fundamentally, all are connected, but you have to take care in terms of point of common coupling is out of the basically near to the demand side, and the point of basically connection is the point in the public supply grid where load is connected, where plant or can be connected. These are some differences. Point of generator is the point of plant infrastructure. This is just name in terms of the grids, so you have to think about that. As I said, power quality wise, DC current injection can saturate basically DC current injection in the utility grid. There should be not any DC current injection in the utility grid. Basically, it will saturate your transformer and leading to the overheating and trips. So this is the power quality requirement and the harmonics. So harmonics normally less than 3%. You can follow the BIS documents now in the form of IEC. You will get the certification as per their requirements. This is the discussion of in terms of the islanding effect. Unwanted standalone operation of grid connected inverters occurs when the PV inverter does not switch off after the grid is disconnected. That is very important. It is continuing to operate with the local load. If the generation matches the local load, the grid voltage does not drop to zero. Hard to detect the identity. The grid disconnection can occur due to local equipment failure or intentional disconnection for servicing. Okay. So prevention of standalone operation is very important. And what's how they do? They will do by the passive method, active method, or utility methods. So I have not gone through the PLL and other loops, and this is the Now, in summary, PV inverter must follow the certain technical requirements before they are permitted to feed into the power supply grid called grid codes. So we have also our codes. So sun spec, if you go and follow that, now India is also developing our own sun spec. So that is online available. You can go. It is in development stage. So grid type PV inverters most tolerate certain
Hello,
grid
Aman
voltage.
sir.
Yeah,
So,
yeah, please. Huh.
hello, Aman sir.
Yes, yes. Tell me. Hope I audible?
Aman sir,
Yeah, yeah. Am I audible?
are you there? Aman
Yes,
sir.
yes, yes, yes. I'm there.
You are audible, sir.
Yeah, yeah. I'm audible. Yeah, yeah.
Yes, yes, you are audible, sir.
Yeah, yes, yes. Maybe Anjani is not.
Uh,
I think we lost the connection with Aman sir.
no, Anjali, sir.
Hello, Aman sir.
Yeah, yeah, yeah.
So, Anjali, sir, you reconnected. Yes.
I think Simranjit, I'm audible to you, na?
Yes, sir. Yes, sir. Audible, sir. Audible.
So other participant also.
Yeah.
Yes, sir, audible.
Okay, okay.
Sir,
Thank
audible.
you.
You are audible, sir.
Thank you. Thank you. So basically, as I said, you have to, if you are designing inverters, PV inverters for grid kind of application, you can, even non-grid also, you can go and follow the BIS norms. So that BIS norms is not new, that is generated from the IEC norms. And also there is the software norms made, that is from, that is sun spec. If you go and google it, that sun spec is developing, and you can understand that for the commercial application, commercial purpose. If you are designing your product, go to the market kind of things. So in summary, grid tie inverters must automatically switch off when the grid is disconnected or tripped to avoid safety hazards. Okay, and the grid tied inverters, I think it is not written in summary. Grid tied inverters are basically hybrid inverters. They works with four combinations. One is through the panel, battery, load, and grid. So your electronics has to take care all four and supply the power and transfer the power as per their need. Those, that is grid tied inverters. So that is the little bit complex, and I think this way I think I have covered almost all. In summary, we can go again first slide. So we discussed all PV power characteristics and their loading techniques. What are the loading which required? What are the loadings are available? And their tracking, how to track maximum power. Then their power converters, in their application, it is combination of DC-DC and DC to AC. Then separately DC to DC converters we discussed for solar. Then inverters basics, then their inverter types in terms of the off grid, on grid, means number of series, parallel, and all their naming and their conventions, and then interfacing of the grids. I think in 1 hour I think cover most of the things. So thank you everyone. We can discuss. If you have any questions, and again we can go to slide by slide also if you feel some speed is there.
Sir, Hello, sir. So, do
Yeah,
we have some met, means using this techniques we used? Can we implement it through MATLAB? Or
yeah. All work basically, if you design anything, na, it will start from the MATLAB.
okay.
So I
So,
thought you people have already covered that thing. That's why I am not put here. So basically, this all design thinking. If you start prototyping the things, so first do the simulations, understand everything, and that MATLAB is has very rich library, and you can use it, and depends on the specification. You can test it also, and finally after prototyping and all, you can make the final products. So that will be there definitely. Otherwise very difficult if you are going with higher wattage system, more than maybe kilowatt range. If you hear megawatt also is there, so then without simulation, without digital twin, it is not possible. And now MATLAB is good in terms of they have also embedded AI, so that will be great help.
okay, okay, sir. So, so digital twin, I think, is implementing in everywhere in the industries also, sir.
Yeah. Digital twin basically it will give the idea beyond the simulation.
Yes, sir.
So simulation already you are do just understanding purpose, but you want to go deep dive. I had one lecture with your university only, so I
Okay.
explained the what digital twin is. So that is the next level. So MATLAB is of course without MATLAB, and I think there is the power electronics separate tool. You cannot do that.
So we have separate toolbox also for this PV.
Yeah. PV toolbox also there. Power
Okay,
electronics.
okay, okay. Thank you, sir. Thank you so much, sir.
Thank you. Yeah.
So, Anjali, sir, you can.
Thank you, Aman sir, for this wonderful lecture.
Thank you.
Thank you so much, sir. And sir, I have one query regarding can we also able to calculate or estimate the efficiency of any design system in MATLAB? Is there any particular tool for that?
Yeah, it is there already. You can in simulation, if you put
Okay,
your component details, each
okay,
and
okay,
every details, then
okay,
you will
okay.
get the overall efficiency. Again, it will match with your output also, actual
Output also.
product also. Yeah.
Oh, okay, okay. So
And for
whenever,
solar, it is
yeah.
very important. Without
Oh,
that, you
yeah, yes,
cannot
sir.
release your product for BIS certificate. You will not get the certification.
Yes, sir. Yes, sir. Yes, sir. Okay, okay. So all tools are there, like for the power measurement, active power, reactive power, and the efficiency calculations. All are there in the MATLAB and Simulink one.
Yeah, all are there. Even
Oh,
they have the tools for means porting of the code also. Maybe
oh,
you
great.
run embedded
Okay,
coding.
okay. Great, sir. Great. Thank you, sir. Thank you so much, sir, for this wonderful
Thank you.
lecture,
Welcome. Welcome.
sir.
Okay. Then
Okay,
anything
sir.
else? Should I leave?
Yeah, sure, sir.
Yeah.
Please.
Thank you.
Thank you so much, sir.